That's working now. That's good. Be nice when we don't have to do all this anymore. Okay. We have been talking about chapter 10, and one more person wants in. We've been talking about chapter 10, and in 10.2, the book does several things. We've had a little time to go through some of them. Yesterday, we talked about first and second derivatives. If we assume that the parametric representation also has a y equals g of x representation, you guys now know about that. And we talked about the formula for arc length. We talked about the formula for area. And the only thing we didn't really have much time to talk about would be the formula for surface area, which from the other chapter, it had this kind of formula attached to it if we were going to rotate around the x-axis and we were rotating something from A to B. As you know, the surface area is what this formula talks about. And what we're doing in this parametric representation is we're saying x is some function of t and y is some function of t. And what happens is that when you make the change of variables like I did yesterday for the area, then when I have f of x here, everybody knows y is f of x. So when I replace the f of x, it's actually replaced by y of t. Now, if you remember, the author used little y here sometimes anyway. And so if little y is y of t, now the author's going to say, see, that's what you get. You get little y, that's y of t. He's happy. Okay. And the other formula, instead of the arc length being this, when you work out what this is, it turns out to be x prime of t squared plus y prime of t squared. So it's the same as the arc length formula. And we're doing this on the parameter. So if this situation is set up again with a parameter, then the t is the parameter. You have an alpha beta here instead of an a and b. And so the endpoints are going to turn out to be alpha beta. So this is a very similar formula to what you had before. So if you remember 2 pi radius, this is the same idea. We're going around the x-axis here, same formula. And essentially that's the other thing we didn't have time to talk about yesterday. Then there are exercises about these things, but they're all essentially what you come down to is seeing that it's applying 3 or 4 different formulas. And the different formulas are like the formulas you had in the previous chapter 8. So hopefully there's not that much to learn. It's just a translation over to a more general environment where we're describing curves this way. Now, if we had time, and we might have some time towards the end of the semester, I don't know. The study of curves is a much more complicated idea than just this. And what we're interested in a lot of times is measuring a curve with respect to its arc length. In other words, using where you are depending on the length of how far you've traveled. And that representation is what you do when you are on an interstate highway where you have mileage markers. The mileage markers tell you how far you are from the beginning of the region, in this case, a state usually. And so when you see a mileage marker, it tells you how far it is to the state line, not the straight line distance, but the distance along the curve. And it might be to the other state line at the other end of the state instead of the one that you think of. So you may think I'm only 10 miles from the end of the state on the highway, but it might say 300. That's because it's measuring from the other end. But measuring along a curve by its length is a very good way to do it. And it turns out that when you study curves, we want to study them with respect to arc length. What you'll see in other books, whenever they start talking about arc length, they use S instead of X. And so when you see a DS, you know somebody's trying to talk to you about arc length. And if we have a little bit of time at the end, I'll try to give you some more information about that. When curves have a finite length, they're called rectifiable. And the problem is, if you think about certain curves, like the sine of 1 over x, if I multiply this by x, and I look at this curve, what you will find out when you study such things, and we already talked about this, at least I think we did last semester, what happens is that the sine function gets as high as 1 and as low as -1. And when it is 1, for whatever x for which the sine is 1, it goes up and hits this barrier, because this is f of x is x. And what will happen when you study this is you get the graph is constrained to lie between two things on both sides. It happens on the other side as well. And the question is, if a thing's going to oscillate more and more and more, is the length of the curve finite? Or is this a curve of infinite length? And this is the kind of question that people worried about at the end of the 19th century and earlier, but they worried about at the end of the 19th century again, because in the late 19th century, they learned what real numbers are. And once you learn what real numbers are, you can start talking about what length means, because it has to do with real numbers, okay? And so forth. So anyways, such curves like this are fairly simple to figure out in terms of their equation that you use to describe them. But as when it oscillates more and more and more, the question is what you end up with something of finite length or something of infinite length? Well, we could answer that, but I'm not going to answer that right now. There's another thing that is possible with parametric situations, and that is that it's possible to take a thing like this and describe a continuous function that fills in every point of a rectangle. And that was considered impossible, but it's possible. And so it is the kind of question where, and what this is called when you define such a thing, is called a space filling curve. So it's a curve that fills up the space. All right, every point is a point on this curve. So it no longer has just a one-dimensional thing, it becomes a two-dimensional thing. As I said, this was not believed. And it's one of the reasons people had to study curves more thoroughly, because this kind of thing, and one of the people who dealt with this was named Peano. Okay. Anyway, there's lots of stuff about curves we haven't had any time to get into. For us, we don't have to worry about the stuff I'm erasing here. I'm not going to ask you about the length of things that, when they might be infinite, but it's an interesting study that you might find. And we do more of it in Calc 3, if you take Calc 3 honors anyway. Okay, so what I want to talk about today more is, first, well, we should talk about a test over, I'm trying to think, this is Wednesday, you've got a test tonight that's due, right? And that's a test over chapter 7. And we are right now in chapter 10. So we've also talked about chapter 8. We need to take a test in chapter 8 as well. Okay. Now, what I think we should do again is take it as soon as possible. We'll give you a little leeway. But originally I thought about doing is having a test available Friday and having it due a week from Friday. The question is, would that give you enough time if you took the test next week? Okay.
So made available this Friday.
Well, or so. I mean, that's what we're talking about.
And then due the next Friday.
Right.
All right.
If that would be a test in chapter 8. And this is Wednesday, maybe we can talk about that on Thursday or Friday. Okay. Then for those of you, once you finish this test, you might have to take a second test in this material in chapter 7. We'll have to schedule that too. Okay. But I don't want to keep pushing off tests because we're not in April yet, but things do march on. Okay. Where I am at the moment is section 10.3, and it's about polar coordinates. Now I want to ask you guys, how many of you have never studied anything with respect to polar coordinates? I'm looking at people in here, 2 or 3 people here out of about 10. What about you guys at home? Anybody? There are 10 of you at home there somewhere. That's a lot of people.
If I did, I don't remember.
If you did, you don't remember, okay. Anybody else brave enough to say that?
Me.
Yeah, okay. Well, we'll talk about it. Again, if everybody said, oh, I had that in high school, then we can do more stuff, okay? When it's like, oh, yeah, I don't know what you're talking about, then we gotta go a little slower. Okay, so just generally, what we have been doing is putting a coordinate system on the plane by deciding where 0 is, and points in the plane turn out to have 2 components because we already talked about chapter 12 and we know about vectors and stuff. Anyway, when you put a coordinate system on something, you're then trying to address everything. Like in Wichita, you have Broadway, okay, and you have Main Street and you have Emporium. Those are streets that go north and south. And you have Douglas and you have other streets that go east and west, okay? Well, somebody had to decide what is point 0. Where do you start the addressing system? Because addresses are numbers and streets. It takes 2 things. Now, we could just do 2 numbers. We could say 2, 5, and that would be 2 this way and 5 that way, just like we do in math. But what we normally do is we say 200 west something, and that gives you a distance one way and maybe a distance another way by identifying 2 separate concepts. And if you live in an apartment, they might say 3rd floor or something, and that actually puts you in a 3rd coordinate system because it's a 3-dimensional system. Okay. Now, when big cities swallow up small cities, a lot of times the small city had its own addressing system. And so you may find, and I don't know much about Derby, for example, but you might have found 100 years ago, maybe Derby had a main street. I don't know if they have a main street or not today. Anybody live in Derby? I don't think they do. I think Derby uses, for example, Oliver. I think in Derby you can live on Oliver Street, and that's a street in Wichita. And so if you go down Oliver, you pass the aircraft industries and stuff, you keep going, you'll hit Derby sooner or later. But they kept the same street name, I believe. Yeah, I'll understand. And if that's not true, you understand what I'm trying to say. So when you have a big city swallow up a small city, or when the small city is close to the big city, they might have their own addressing system, or they might incorporate your addressing system. Okay, so you have Goddard and you have Mays and so forth around the city of Wichita, Keachai, and so on. And some might have their own addressing system and some might not. You also have a city within a city. As you know, on the east side, we have a city, and they had to decide when they incorporated whether or not they would use the Wichita system or not. Anyway, why am I trying to say worry about all that? Well, because there's another way of defining where you are on a plane, and that is to decide, first of all, some idea of what's horizontal, okay? And that's relative, because we might say this is horizontal. And depending on your circumstances, maybe that's horizontal. If you're lying down, maybe you think that's horizontal, okay? In the event, you decide what's horizontal and you decide where you're starting. So again, what I'm going to do is use 0, 0, but 0, 0 might not mean the same thing as it did in the other picture. Okay, but it's called the origin in either case. And in this world, we place points by asking, once we have this system's done, and let me compare now, with this one, we have two things decided. We decide what's horizontal and we decide what's vertical. Once we make that decision, that determines, the intersection determines the origin, and we base all the addressing off of that system. Okay, well, with this one, we have a point here. We want to address it. We want to assign some place. What we do is assign its distance from the origin, because that's one thing that places you. And if you think about it, then suppose I said I live 1 mile away from you. Okay, if we don't have streets, if we just have land, that would put me on a circle somewhere. Now, when we put in rectangular streets like you do in most cities in the United States, it kind of confuses you if I say I live a mile away, because maybe it means when you drive one place to the other, the odometer says 1 mile. But that's not a circular distance, that's a rectangular sort of jagging back and forth distance. In Europe, and in some places, it depends what country we're talking about, sometimes they did not plan the city. The city arose before they made ideas about planning rectangular streets and stuff. In Paris, for example, Paris, in a sense, the streets were kind of a mess until you had a man named Haussmann come in and redo all the streets. And if you know anything about Paris, there is a place, and it has a name, and that means star, and that's because there's a nice statue here, and you have a Champs-Élysées, which is a main street, but this thing is a circular thing. You'll have traffic going around this way. Anyway, you have streets coming out from this, and it's called a star. Off of that, you have other streets that are irregular, but you have these kind of things that have to do with a star. Okay, if any of you have been to Paris, this is one of the places you visited, because this is the main street, and this is the thing everybody goes to see, the Eiffel Tower down here, and so on. But basically, there was a man that decided how to redo all the streets. And so Paris is very well laid out now with north and south, east and west, but they had to do that in like the 18th century or something in order for it to work. Well, some places have never done that. And so I have found in my own travels that some people, when you ask them about north, south, east, and west, they're not used to thinking that way. Whereas if you say to somebody here, I live north of you a couple of streets, everybody understands that kind of thing in the United States, because everything is based on that system. In the United States, most addresses, like in Wichita, if you're on a north-south street, the odd numbers are on the west. The even numbers are on the east. If you come from my hometown, which is Indianapolis, the odd numbers are on the east and the even numbers are on the west. It's a switch. Where I come from, First Street comes before 100 numbers. In other words, if I live on the corner of First Street, I'd be at 100. In Wichita, you're at 200, because they use the end of this numbers to be the name of the street that has that number. You all understand? So I get confused because I grew up in one city where if you said I live just north of 21st Street, that would be okay. But if I say I live at 2100, 2150, in Wichita, you go south of 21st Street. In my hometown, you go north of 21st Street. And so what you have to do is you have to get used to your coordinate system so you don't get lost. Okay? And my problem was I got to know the Indianapolis system very well because I worked in the post office for 5 years delivering mail. So I learned the system very well. I can find any place in Indianapolis. But in Wichita, I have to reverse some of my thoughts. But by the way, east and west is the same as Indianapolis. So one way is switched and the other way is not switched, and that can cause you trouble when you're driving too fast down a road trying to find an address. Because I sometimes turn the wrong way and then I have to make a U-turn or something illegal to turn around. Anyway, okay, so what's all I have to do with this? All right, well, we have a second way to do things, a distance and an angle. And so if I tell you what angle I am away from the horizontal, and if I tell you how far I am from the origin, those two things will exactly put me at the same kind of place as I would get if I told you how far I was along the horizontal and how far I was up the vertical. You have the same kind of system, sort of. And the reason I say sort of is because this idea of rectangular, you have a one-to-one correspondence. Every pair of numbers is exactly 1 point, and every point has exactly one pair of numbers. But with this idea, okay, if I go around this circle once so that the angle is all the way around, now I'm ending up at the same spot, but I have two different angles that tell me about it. Okay. And the other idea is if I allow not distance, but the absolute value, you see, something out here is the same distance away as something here. And as long as I restrict myself to numbers having to be positive distance, those are different. But if I allow the R, because we're going to talk about R and theta. The theta I've already told you about. The R, if you allow it to be negative, then I can say go in this direction the opposite way. And so I might say this is -1 something if this is the angle and I put that angle down, I can back up and go the other way. And so the point is I can have an infinite number of addresses for 1 point. That's different from the rectangular. So we have to be careful. Okay, we have to decide, okay, either I'll make R always positive. It depends on how we want to use this system. And it turns out in certain situations, we want to make the R always positive, but in other situations we don't, and that's part of what we're going to be talking about. Okay, so if I take these two things, there's another way of talking about this, and that is something, and this is not in the book, okay? I might want to take my rectangular system here, if I call it R2, and if I call this R2 as well, okay? I might want to take each XY and decide what R and theta it is. Or I might want to start, now you won't be able to tell here the difference for a second. I might want to start with the R theta world, and for each R and theta, I might want to have an XY. In other words, if I have a point and I want to describe it by both systems, how are they related? Okay. If I know what X and Y is, what's the R and theta? Or if I know what R and theta is, what are the X and Y? Okay, well, part of that's pretty easy. If I go to this world here, where I have an X and Y, and I decide to make R this distance across here, then R is going to be X squared plus Y squared square root. And that relates, if I know X and Y, I can find R. Okay. And if I measure this angle, how do you measure this angle? Well, the tangent of this angle is y over x. So if I know x and y, then the tangent of an angle, if I make that y over x, that tells me sort of what the angle is. Now I said sort of because it doesn't tell me the angle, it tells me the tangent of the angle. So how do I find the angle? The natural thing for you guys to say is that angle is the arctangent. But unfortunately, that's not true. Remember, the arctangent was only defined for a cut down version of the tangent, so we had a one-to-one function. Remember, the tangent graph of the tangent function looks like this, but then it repeats itself and it repeats itself. It's not a one-to-one function. So for every angle, for every x, you have lots of tangents. And therefore, you don't uniquely identify an angle by saying what its tangent is. It lets a lot of other things in besides. So if you want to say arctangent, that's only going to be good if the angle is acute. Because the tangent is only defined between minus pi over 2 and pi over 2. We cut it down to have an arctangent. So you have to be careful. So the description in terms of arctangent you can do, but it takes three different things here to describe the angle. It depends on how big the angle is. All right, and I'm not going to take time to do that today, but the tangent is pretty simple. So we describe it in terms of its tangent, but we then say, be careful of what quadrant you're in, because that's going to make a difference as to what the angle is. So if you happen to be over here in the second quadrant, okay, the tangent in the second quadrant is negative. But if I happen to be in the fourth quadrant, the tangent in that quadrant is negative. And so you might not know which you're in. In the third quadrant, the tangent is positive, and the first quadrant is. So you've got to know what quadrant you're in to decide how to relate the y and the x. So if you know you're in the third quadrant, you're going to pick an angle that's in the third quadrant. Does that make sense? So you can write down rules. If x is positive and y is positive, then you say one thing. If x is positive and y is negative, you say, and so on. Okay. So anyway, what I wrote here, though, that's saying I'm talking about a function that takes everything here to over here. But see what I did here, notice I put a theta and an r on top. What I did, this is supposed to be the, right now, the theta r world. And that over there is a rectangular world. But if I think of theta and r as rectangular, if I would do something like this, now I'm not thinking of theta as an angle, and I'm thinking of both as numbers. Now, so let's think about that a second. Suppose that I have a world, and it's going to be the second world right here. Suppose I have an r theta world, and I take something where r is constant, like r equals 1. In a rectangular, if I view r and theta in a rectangular world, and I say r is constant, okay, rectangularly, and over here, I'm going to be in a world where r and theta are these angle and distance things, then r equals 1 becomes a circle over here. In the xy world, a number r equals 1, where I view the r theta as a rectangular world, and I view the xy as a rectangular world, r equals 1 in that world becomes a circle in this world. Because in this world, r is x squared plus y squared square root. And what does theta equal a constant become in this world? That says the angle is constant. If the angle is constant, you get a line. If the angle is, let's say, pi over 2, then I would get this line right here. Does that make sense? Because the angle, if I interpret the angle this way as an angle, pi over 2 is that right? If the angle is constant, so what if it's pi over 4? Then I will get this line. So we are used to thinking rectangularly. If I gave you r and theta and just said plot it and you put it on a rectangular picture, you would still get r equals constant would be a vertical line. But if I want to think of it as a distance from the origin, then I'm in a rectangular world, but I'm viewing the r as a distance, and that gives me a circle. So viewing it that way is called viewing it in polar coordinates. And what we do is we take the two pictures and we put one on top of the other. And that gives us this picture here. Here we have an XY world and we have an R and theta world on top of each other. Why do we put one world on top of the other? Because when I have functions that go from 2 dimensions to 2 dimensions, the graph would be 4-dimensional. And I can't see that. Now, think back, when I have a function from 1 dimension to 1 dimension, we make a graph by putting a pair, and you get a graph. Okay? But if I have 2 dimensions to 2 dimensions, the domain is 2-dimensional and the range is 2-dimensional, and I want to make a graph by putting the domain and range together, I'd have 4 coordinates. And we humans can't see that. So what we do is we superimpose one on top of the other. And that's what you get when you say, I want to think in polar. You're still thinking in rectangular. When I say, I want to think about where something is polar coordinates, you think about the angle and the distance, not the rectangular 2 numbers. Okay? So what we have is a conversion thing, and so I'm going to get off of this stuff right now. When you get to Calc 3, we're going to study functions that do this. Take you from 2 dimensions to 2 dimensions. Right now, we're not. And so we have r is the square root of x squared plus y squared. That's one way. And we have the tangent of the angle is y over x. Okay? Now, so if I'm given y and x, I can figure r and theta. What if I'm given r and theta? How do you find the x and y? Well, r times the cosine of theta turns out to be x, and r times the sine of theta turns out to be y. Why is that? It's because when I have an xy and I have an r, I have a theta, that the number here, the cosine of theta is this number over that number. So how long is this? If x over r is the cosine of theta, then x is r cosine theta. And that's what I wrote right there. So this x is r cosine theta and r sine theta the other way. So now we have a relationship. If you tell me r and theta, I know x and y. So part of what you do in section 3 is you say, okay, I have a point 2 pi over 4 in polar coordinates, not rectangular coordinates. So you have to tell me, when I see a pair, I don't any longer know how to measure. Normally, when you see a pair, you go over 1 and you go up 1. Not one value, but one thing. If I tell you I have this as polar coordinates, that tells you r is 2 and angle is pi over 4. Now you got to be careful, because some people, maybe us, we'll have to see, some people describe the pairs where they put the angle first. Okay? So if you think this is the angle and this is the distance, you're going to have a different place than if you think this is the distance and this is the angle. So we have to decide, are we going to do an r theta or are we going to do a theta r? You need to figure that out. Okay? Because all the answers in the book are going to do it a certain way. So how do we view this? I need you to look in the book and figure that out so that you'll know it, not just me tell you. Now, on the other hand, if I said to you, this is r theta today and tomorrow I said this is theta r, you'd understand. But we need to tell you something so you know how to interpret the pair. Now, so suppose this is now r and theta. How would I find the rectangular? I would stick the r right there, 2, and I'd stick the theta right there. The cosine of pi over 4 is the square root of 2 over 2. 2 times that would be the square root of 2. So we'd be the square root of 2, square root of 2. This would be where we are. If we're on a line that's pi over 4, that's, that's a diagonal 45 degrees. The y equals the x, that's why these two things are equal. So what do you do in section 3? You do some conversion. Give you xy, tell me what r theta is. Give me r theta, tell me what xy is. Okay, web assign, they give you some of those things to do. And he shows you some angles and stuff, and that's all pretty easy. Where it gets interesting is starting on page 700, where they talk about polar curves. Now, this has nothing to do with being very far north. Okay? Because polar makes you think sometimes polar bear, something. In German, polar bear is an ice bar. Okay. So in German, when they think of a polar bear, they're thinking of something that has ice. It's even more. Here, polar bear doesn't mean far north. It means in a zoo, maybe. But if you say ice bar, now we're thinking about something cold, right? At least, maybe. You say bar, you're not thinking about something, you're thinking about something else that's a different part. Anyway, the graph of a polar equation. So, what do we mean if we say y equals f of x? Okay, that's what we say with a function. What if I have r equals f of theta? Now, if I know nothing about polar coordinates and you give me these two things, I think, well, for some reason, they want me to put theta for the x and r for the y, and you would graph, if I said f of theta is theta squared or something, I think you'd graph a parabola. Because you see this as rectangular, because that's what we've been doing. But we don't want you to do that. When we say this is a polar equation, we want you to think of the theta as an angle and the r as a distance. So we're going to superimpose things on the xy world by interpreting the variables as polar coordinates. So, for example, what if r equals 1? We've already talked about that. You get a circle. If theta equals 1, we would have an angle of 1 radian. All the points on an angle of 1 radian. So the simple equations for polar coordinates are when the r is constant or the theta is constant. In one case you get circles, in the other case you get lines through the origin. Now, if r can only be positive, you wouldn't get a whole line through the origin, you'd only get a ray through the origin, stopping at the origin. Okay? So I told you you have to decide whether the r is positive or can it be negative. Okay, if I'm saying theta is pi over 4 to make it easy, and r has to be positive, I only get this. Because the distances are all if the angle is this, I don't get this down here because how do I get down there if I only go positive from the origin? Okay, if I allow R to be negative, then I get the whole line. And depending on the circumstances, we have to decide which one we're in. Okay. So what if I have more complicated things? Like R equals cosine theta. What's the polar graph of that? Well, now we're back to plotting points because we haven't yet developed any techniques for maxima, minima, increasing, decrease, you know, all that stuff you do in Calc 1 with functions. Ain't got it. All we got is a formula relating the two. So what you have to do is plot points. What people normally start doing is saying, okay, R and cosine theta. So if R is 0, this is 1. If R is pi over 2, this is 0. So let's see if I can figure this out. Cosine, when R is 0, the cosine of 0 is 1. So if R is cosine theta, no, I got this backwards. I should be saying the angle is 0. When the angle is 0, oh boy. So I ought to be, okay, I got to think of which is the independent variable, which is the dependent variable. This says R depends on theta. So you guys wouldn't make that mistake if it was XY, you put the Y second because the Y is what you're going to determine if you know the X. So when we do this, we do the theta first and then the R this way. Now, if theta is 0, if the angle is 0, the radius is 1. Boy, I almost messed that up. But I'm trying to keep you guys from messing it up. Okay? If theta is pi over 2, then the angle is 0. So now we can plot 2 points. If theta is 0, that's along the x-axis, then R is 1. If theta is pi over 2, the R is 0. Well, that's not going to tell me much about the graph. What about 60 degrees? What about pi over 3? The cosine of 60 degrees is a half. So if I go up 60 degrees, well, that's hard to do. Here's 45 and maybe this is 60. So that brings up something. What you can do is buy polar graph paper. Polar graph paper doesn't look like rectangular graph paper. It looks like circles and angles. So that if you're trying to plot different angles and different distances, what you'll have is graph paper that has various angles on it and various circles on it. And that way you can plot accurately polar coordinates. Okay? And maybe I say buy, maybe I can provide you with some. I don't know. Depends on whether I like you or not. Anyway, if this is 60 degrees, the thing is a half. If this is 1, then a half would be about here. And so on. And we're running out of time. It's 18 after or so. Anyway, what you'll find out is you'll get a graph that looks like this. Now, I have just enough time to say, well, suppose that instead of that, is there anything I can do here? Like if I would make R square R cosine theta by multiplying by R, okay? Then this is x squared plus y squared, and this is R, x, this is x. Then x squared minus x plus y squared equals 0, and that's x minus, if I make complete the square here, I'll get x minus 1/2 squared plus y squared equals 1/4 or something. And what do I get? I get a circle. And the center is at a half. And height 0. The center is here. The radius is a half. And so if I can convert from the polar to the rectangular, I get a circle. So this particular equation in polar coordinates gives me a circle, but not a circle centered at the origin. The circle happens to be over here. What do you think you get if you have r equals sine theta? You get another circle, but this circle is going to turn out to either be up here or be down here. What happens if I have 1 plus a cosine theta? Now it's not going to give me a circle anymore, it's going to give me something else. Anyway, what we've got to do next couple of days is play with graphing polar stuff. And it's a lot of fun if you have the right medium to draw on, because we will get heart-shaped things. Some curves will give us cardioids. We will get snail shapes, so-called. They're not called snails, they're called something else. In French, the French word is what we will use. I won't tell you what that is yet. Anyway, we get different pictures that we never got before by viewing things as polar instead of rectangular. And that's what section 3 is about. So today I just wanted to kind of introduce it. And I've got some handouts that I may give to you to tell you about things. But we have all kinds of strange names that come out. Here I have on page 702 a 4-leafed rose. That's a pleasant thing to draw. A 4-leafed rose, a 4-leaf clover. That's good luck in a lot of countries. And then if you look, and it's hard to do here, but because 21 after also, but if you guys at home can look on page 705, you will see all kinds of nice pictures that we get that are all based on circular kinds of stuff. I don't know if you've looked at this section, there's some of, where is this upside down? Over here. These are nice pictures you can get that would be very hard to graph by hand. I don't know if you can see this. Anyway, look in the book. It's a new topic, something we haven't considered before. And if you guys haven't done polar coordinates at all before, it's a whole brand new idea. I'm going to stop the recording here to release